In any case, so let me talk about some generalized magnetization properties. So basically, the idea is to try and come up with a sort of very quick, how does a magnetic field affect the properties of matter, and why do we care about it at all? Let me get the right thing here. Okay, so basically, I'm going to talk a little bit about bulk magnetization. That's relevant because actually that's what we image. There are two kinds. There's diamagnetic and paramagnetic. Diamagnetic comes from when you stick a molecule in a magnetic field, the electrons respond. If you put a ring of current in the magnetic field, the current, you'll induce a change in that current to oppose the magnetic field. So the response in a diamagnetic case is to reduce the field, basically. Paramagnetism comes from things called magnetic spins. Well, spins, angular momentum, that are charged. Well, they don't actually have to be because the neutron has a magnetic moment, for example. But I don't want to get into the complications of that particular problem. But so if you have a spinning charged object, you have some actual magnetic moment which interacts with a magnetic field and gives you energy. And there's something called the gyromagnetic ratio, which relates the spin, angular momentum, the angular momentum, and the magnetic moment. And there's a whole range of science, physics particularly, that involves measuring that. And one of the things about paramagnetism that people noticed a long time ago is something called Curie's Law, which I'll explain a little bit and try and explain why that happens. And then there's the next question is, okay, so you have this response to the magnetic field. So I have an object which has got a slightly different field inside it than outside it. So what? How does that affect things? What difference does it make? It turns out the geometrical effects become significant and important, and it's useful to know. They have, for example, are a real pain in the butt if you're doing EPI or anything like that in the head because they're air tissue interfaces, and that causes problems. A little bit, a very little bit about relaxation mechanisms, which is to say, how do the spins go back to equilibrium from whatever you've been perturbing them at? Some stuff on chemical shifts, and a little bit about J-coupling, all of which have to do with the way the the nuclei in molecules interact with one another. Oh, and so let me reinforce Joe's comment about please feel free to ask questions. I mean, we're not that many people that we couldn't have an intimate discussion about it. Okay, so I more or less explained this already. So you have these two kinds of materials, diamagnetic and paramagnetic. Diamagnetic reduces the field, paramagnetic aligns the field. And the reason that, so here's Curie's law, for example. So Curie's law says that the magnetic susceptibility, which is to say how much the the substance responds, depends as one over the temperature. It's a really strange thing, only in paramagnetics, not in diamagnetic. So how does that come about? Well, here's the energy difference between a magnetic, I do have a pointer here, between a magnetic moment on the magnetic field. It depends on the dot product between the moment and the B field. I have asked you to take some of this on faith because there's a lot of material to cover, and this is a lecture that I normally take an hour to go through some of the greater details, so it's a little hitting the high spots. So essentially, this is the gyromagnetic ratio. This is the angular momentum. That's the mu is now that. And so it depends on the angle between the magnetic field and the angular momentum spin in this particular case. Now, you probably know that, for example, spin 1/2 particles, due to quantum mechanics, have two spins. They can either point one along the field or against the field. So for spin 1/2 particles, that S dot B term basically can either be, this plus or minus. So you have two states of the spin, which are either aligned, parallel, or anti-parallel to the magnetic field. And as the field gets bigger, the energy difference gets further and further apart. Now this distance, this energy here, is called the Larmor energy, the Larmor frequency, which we can relate energy to frequency just by dividing by h bar. So as the field gets bigger, this gets bigger. And to give you some idea, in a modern imaging magnet of, say, 3 Tesla, the protons, this separation in protons is about 120 megahertz, roughly. All right? So it's not a very big thing. But the reason it's really useful is it turns out that the... Shoot, I keep pushing the wrong button. It turns out that the lifetime of these levels is on the order of seconds. Now, if you think about what that means from a point of view, you can measure. It means you can measure the energy precision to about 1 part in 10 to the 8th or 10 to the 9th. So that means very small changes in the field makes a big difference in the resonant frequency, which is basically why I'm giving this talk, because everything I'm going to talk about has to do with small changes in the magnetic field due to the response of either the molecule involved or the geometrical shape that I've put into the magnetic field or anything along those lines. So even though I'm only changing the magnetic field by a parts in a million, or maybe even a few 0.1 part per million, that's a substantial fraction of how much I can measure this. Because in point of fact, if the lifetime is a second, I can measure that to about 1 hertz, which is 1 part in 10 to the 8th. So if I shift the main frequency by 1 part in 10 to the 6th, I see it easily. So that's the basis of imaging. It has nothing to do with Boltzmann's effect, I have to say. It was just a digression because it seemed to be relevant. Okay, so this is just some calculations about what this is the energy difference. That's again the Planck's relationship between the energy and the frequency in h bar. So as I said, at 1.5 t, it's about 65 megahertz. So 3 t, it's about 130. So now Boltzmann's distribution, right, which I hope everybody is familiar with, says that the relative density of states in a given energy E is proportional to this e to the minus e over kt, where k is the well-known Boltzmann constant, named for obvious reasons. Okay, so numerically, kt is about 25 million milli-electron volts, which is not very much, but that's a lot bigger than this by about 10 to the 6th. So in other words, this ratio of the energy difference to kt at like 130 megahertz is about 10 to the minus 5. So it's a very small number. So what that means is that e to the minus epsilon over kt is essentially 1 minus that value. All right, you don't have to worry about the exponential at this point, which is really nice. So that means that the ratio of n up to n down, which is this ratio, right, is 1 minus this. And if you work out what that means in density units, it means that you come up with, you come up with a difference in density, which is the ratio of this over that, is essentially the ratio of the B field over KT. So if I put all that together, I discover then the magnetization is going to be the number of different spins times this ratio of this over, there should be a T in here, I'm sorry I missed it. And then you come here and guess what? You have a 1 over T dependence in the Curie law. So that's where the Curie law comes from. It comes purely from the fact that as the temperature changes, Boltzmann's relationship causes more spins in the lower field compared to the upper field. So the difference between the two becomes bigger. And so you polarize the system more because you make more spins aligned. That's only true, notice, for small. It gets, if the temperature gets really cold, then it breaks down. And numerically, right, just to give this in a slightly different way, so you have a higher energy spins versus a lower energy spins. There's more in this state. This is, again, the energy ratio. If you actually put in the numbers, it's something like that. So again, this is another way to say that this ratio is pretty small. And so a typical number is that you get 7 out of 1 million protons are aligned at about 1.5 Tesla. So it's a small fraction. Now we're taking advantage of that. I'm sure everybody's heard of something called hyperpolarized. Sorry, I really haven't been paying attention to the time. Okay. Hyperpolarization is where you manage to take this ratio and put them all down here, right? Or put them all up here, it doesn't matter. Put them all in one of those states. Would I like a real pointer? Thank you. It makes not pushing the wrong button. And not only that, it's green, which means you can see it. So hyperpolarization means that you can get essentially a huge population difference. And notice that gives you a tremendous potential increase in signal to noise, because now I'm not talking about 7 out of 10 to the 6, I'm talking 7 out of 10. So there's something like a 10 to the 5th order of magnitude increase in signal to noise, which is where all the excitement about hyperpolarized C13 and things like that are coming from. Because now the problem is the lifetime between these two states is, again, dimensionally on the order of a second, so it doesn't stay there. It goes back to its happy thermal equilibrium. But while it's around, it's a socking great signal. All right, and there's a lot of effort being put into doing that, particularly with C13, some with various noble gases that you can do games with and stuff. So there's a lot of structure effort going into that. And I think that really falls under molecular imaging, if you, by any reasonable definition. Okay, so now you need to realize that, of course, electrons are also spin 1/2 particles, and so they have and they're charged, so they have a magnetic moment, and they have a much bigger signal. There you're talking about population differences that are around 1% or something like that at normal fields. In fact, they're so, which means if you cool them down to liquid helium temperature, you get 100% polarization because the temperature is now dropped by a factor of 100. All right, but the thing is, it's really hard to get free electrons. But there are cases, and the reason I bring this up is because oxygen will become important in the susceptibility argument in just a minute, where oxygen, O2, the molecule that we all breathe and live on, and it is 20% of the air in this room or so, right, has a unusual ground state in that it has a non-zero angular momentum, orbital angular momentum, which gives it, in point of fact, an effective spin and therefore magnetic moment. And so liquid oxygen is actually paramagnetic, and there's a beautiful demonstration or two. I didn't think of it until this second. I should have looked at it on the internet. There's a movie where you take a vial of liquid nitrogen, which is a beautiful blue color, and bring it up to a magnet. It goes right into the magnet, right? It's just like walking up to one of our imaging magnets with a piece of iron. It'll be happy to grab it, too. It's the same phenomenon. So anyway, so now, essentially, so what do we have in terms of macroscopic magnetization? Well, in water is about 110 molar in protons, right? So that's a lot of protons. And so that means you can treat the whole thing as essentially classically, approximately. We have some very clever spin physics tricks that you can do that makes that all that break down. But in terms of imaging, just thinking of them as a classical moment is a perfectly reasonable thing. Okay, so boundary conditions on susceptibility. I know this is blindingly fast, and I'm sorry, but I don't see any other way to do it. So that you have a B is some ratio on M, on H, so you have the magnetic flux and the magnetic field, that's B and H. So if you talk about magnetization, you can relate H is B over mu naught minus M, and if you wander through this, you come up with an equation that says B is related this way to M. And for small susceptibilities, which is always the case where we have M is some linear function of B with a susceptibility here on psi. So if you look at boundary conditions in electrodynamics, right, it turns out that the component of B perpendicular to the surface has to be continuous, and the component of H parallel to the surface has to be continuous. And when you impose those on geometry, for example, which I'm not going to do because it would take too long, right? But if you take my word for it, if you put a sphere of some susceptibility in free space, then the field inside will be about 2/3 the field outside corrected by that, okay? So there's a change in the field inside basically due to this bulk magnetization, and it turns out for very nice mathematical reasons, which formally has to do with the fact that Laplace's equation separates in spherical coordinates, but it's uniform inside. It's an interesting fact. There's a field outside the sphere which is not uniform, looks like a dipole moment, but inside the sphere it's uniform, which is actually really convenient because otherwise we would have a lot more problems making images. Okay, so if you have a long cylinder, and why am I interested in a long cylinder? Well, for example, it's a good approximation to a blood vein or a capillary or anything along those lines. Long, skinny, approximately constant right circular cylinder. So if I do that, then you can assume if you have some axis to the magnetic field and an azimuthal angle, and maybe I'll show you this next. So this is the geometry. Okay, so the field is this way, you have a cylinder this way. So this is theta, this is phi. So as you go around this way, you have one dimension. As you tilt the thing away from the magnetic field, you have a difference in behavior. And that is given by these equations. I don't want to go into detail. I'm just showing you can get them. And notice that this falls off as you go away from the signal as 1 over r squared. That's fast, but it's not super fast, right? So that means if you have a 10 or 20 or 50 micron vein, for example, for those of you who are interested in fMRI and things of that sort, that means you have changes in the magnetic, significant changes in the magnetic field out to a couple of times that radius, typically. And so that really screws up the signal. That's the basis of the whole fMRI business. And you'll notice also that the field inside, is that me or is that, well anyway, the field inside is also angularly independent and also shifted, which you can see in the right circumstances. And this just shows you some field lines. This is typically what it looks like if you're going, this is transverse, and this is transverse in the opposite direction. This is a sphere. There's really no effect on the sphere, and that's sort of the sphere falls off like 1 over r cubed because it's a single, it's not infinite in dimension. Don't forget this is an infinite thing, which means that the field falls off more slowly. And this just gives you some idea of schematically what this looks like. So this is where the delta chi is a positive, and so you get this and this. It depends. This is this azimuthal dependence going around. It's perpendicular to the external field. This is the same thing, just flipped in sign. Make it slightly easier to see. So you have, when you put a cylinder, diamagnetic or paramagnetic cylinder in a magnetic field, the interior is shifted in frequency, and you have this kind of funny quadrupolar-like looking, four-lobe looking, it's really a dipolar kind of thing. Okay, so now why is this relevant? Well, so here's a sagittal view of somebody's head, right? So you have air in the sinuses up in here, right? Now why do we care? Air is just air, right? Well, as I mentioned earlier, air is actually 20% oxygen, and oxygen is actually 2 times 10 to the minus 6 is its susceptibility. That's pretty big. Remember I said we can measure things easily to fractions of a part per million. So if you have 2 parts per million, it's pretty big. And that's pure oxygen, 100% at normal pressure and temperature. So at 20%, it's going to be 4. Water is about minus 1 times 10 to the minus 7. So water is basically tissue. And this just is an example of so what does that mean? Well, so the scale of field variations, because I have air in my head right here compared to the tissue above it, is of the order of 0.4 ppm, which is about 50 hertz at 3 Tesla. So 1 over 50 hertz is sort of like 20 milliseconds, and you have to give me a little bit of time because it's not really 50 hertz. It's really relevant. It's probably more like 10 or 20 hertz. But so what that means is that when I give my signal time beyond 20 or 30 milliseconds to kind of notice that it's living in tissue that's near an air interface, it's going to start to dephase and I'm going to get a lousy signal. I'm assuming you know how to make images, which is a big assumption, I know, so ask me if you want to know more about that. But this is what happens as you increase the echo time in a slice through the brain. You start losing signal from, and you notice it gets bigger and bigger and bigger as you go along. You start losing signal in the frontal lobes just over the sinuses where there is this sort of gradients that come from the susceptibility variations. And you'll notice you also lose them around the auditory canals. It's the same problem there. You have air going quite far into the brain, and so there are these little dipole moments that, well, susceptibilities, variations, right, which destroy the coherence of the magnetic field. And this just is some, I stole this from Mark Hagee. And so this is microbleeds, and this is an imaging sequence that's set up to be particularly sensitive to susceptibility. I'm not going to take the time to go through it, but it really, you can see, knocks out the front of the brain, and every place where there's a little microblade in this patient is very dramatic. And all of this comes from these kinds of susceptibility considerations and the magnetic fields that you get around the effective dipole moment. Okay, so relaxation mechanisms. I'm going to go through. I've got 20 minutes? I thought I only had 30 minutes to talk. I have 5 minutes. Okay, I'm going even faster now. Okay, so how do we, by relaxation, what do I mean? Well, I want to get back to thermal equilibrium. So I want to get back to my state where everything's in the normal, and I'm not going to tell you how I detect the spins, but basically I perturb them in some way. All right, and so I can make measurements on them until they get back and they do what's called relaxing. And so there are two kinds of relaxation. One is we can change the population imbalance, that is to say the Curie Law population, right? And how long does it take me to get back to the standard one without any problem if I've perturbed it in some way, which is what I do to observe it. And the other thing is that what I've also done is that there's another coherence, which is I'm looking at the spins over, let's suppose the sample's uniform, I'm looking at the spins over the entire sample, and if they lose coherence between one part and another part, I'm going to lose the signal as well, because that's how I'm detecting it. I realize I'm assuming a lot of background stuff here, which is to say the reason I'm detecting the signal is that there's an induced voltage in some coil which is around the sample because the magnetization is rotating, all of which I'm assuming everybody here knows, in which case, if you don't, ask me later. So what that means is that I need to have some fluctuating magnetic fields at two frequencies. One frequency that is the Larmor frequency, so that in fact it can tweak the spin populations. That's something that does what's called longitudinal relaxation. And the other frequency is near zero because I just need to make the differences in frequency between different parts in the sample be not very far off zero. So there are two relevant frequencies. Why is that? Okay, well, so that means I want this and I want that. So how do I do that? Well, basically, the spins are moving around through this solution, whatever it is, or substance, right? And they're bouncing into things, and they're experiencing some fluctuating set of magnetic field just because they run into electrons, or they run into spins, or they do whatever. They're doing something. I don't care what it is, right? So there's some sort of fluctuating magnetic field, and so I don't want to go into the details of that, but suppose that you could imagine sometimes it goes through those fluctuations faster, and sometimes it goes through them slower, and there's some kind of natural coherence time. So if it's experiencing some field strength, it's got some correlation time before that changes in a significant way. That's a typical model of how things fluctuate in the world, right? So that you have, what that means is, okay, so if there's some correlation time which measures how long the molecule takes, we're going to have a formula that looks vaguely like this. There's some average magnetic field, and there's an exponential of e to the minus t over some time, okay? And if I look at the Fourier transform of that, which I need to do in order to get how much power I have at a given frequency, I get a formula that looks very much like this. So at low frequencies, it's constant up till about it gets to the correlation time, and then it starts to fall off like 1 over omega squared. And this is a typical graph of what it looks like at different correlation times. And suppose this were the Larmor frequency. And then there are three regimens, right? There's one where the tau c is much, much faster than the frequency, and it doesn't really matter. It's going to be constant. Then there's another one where, I should say, by the way, the areas under these curves have to be constant because I'm assuming that's this B average squared. So you go from a region where there's a lot of power, some power, a maximum power, and then it falls off rapidly as the correlation time falls. Okay. So what that means is that as you get to longer and longer correlation times, that's this way, right? You start increasing, and then all of a sudden you drop off. Whereas if I'm looking at near zero down here, as I shorten the correlation time, I just keep getting bigger and bigger. So what that means is that you get curves that look like this. So this is T1 and this is T2. T2 is this time that's involved in the dephasing of the signals across the sample, right? And as the correlation time gets shorter and shorter and shorter, all of these, they go up, up, up. But for the T1, for example, you'll notice as it gets longer, right, there's a minimum. This is when the field, the Larmor frequency is approximately equal to 1 over the correlation time. And then as the correlation time gets longer, the T1 just goes out of sight. So for long fixed things, like, for example, solids have long T1s. Not easy to observe. There's a whole realm of NMR that's involved in that. Okay, finish up quickly with chemical shifts. Am I okay? Are we time-wise? Are you? Okay. Joe's a sweetie. Okay, so chemical shifts. Actually, chemical shifts are the reason MR is actually here in the first place. It was discovered after the war, Second World War, I should say. For those of us Joe's age and I, when you used to say the war is obvious what you meant. These days, you say the war, who knows? Leaving politics out of this, however. So what happens in a molecule? When I put a molecule in the magnetic field, the electrons shift slightly. Again, this susceptibility effect, and they actually shield the nuclei from the external field. That means the resonant frequency of the nuclei is slightly different, depending upon the molecule. And it turns out, right, it turns out that the orientation of the molecule makes, unless it's a symmetric molecule, of course, but most molecules are not. So there's something called a chemical shift anisotropy, which means as I rotate the molecule around, I get a different frequency, right? So, and obviously, you can imagine it depends on the number of electrons. So if you have a nucleus with like phosphorus 31, and you've got a bunch of electrons around it, then it's going to have more of an effect than for a proton, which only has one electron, just naturally, because the electrons are going to add up. So if I took a powder of a crystalline amount of material, so that I now had a bunch of different orientations, and I threw it in a magnetic field and I asked where the resonant frequencies were, I get a very complicated shape looking like that, which I'm not going to go into explaining, except what it's made up of is individual lines at different orientations. And this has to do with a symmetric kind of molecule, an axial symmetric molecule, and this has no symmetries at all. Now notice, and this is why it's relevant to chemical shift, if you tumble this all very fast, so you jump around all these orientations very quickly, like, for example, a molecule in solution goes, reorients itself, oh, I don't know, 10 to the minus 13, 14 seconds, depends on the molecule and the temperature and a few things like that, but it's a very fast reorienting process. That averages out to a single frequency. That's called the solution chemical shift. And that actually turns out to be amazingly useful. And the reason that it's amazingly useful is that it depends on the detailed chemistry where that is. And here's, for example, the typical proton chemical shifts. And so these are the various kinds of bonding structures that you expect to find protons in organic and inorganic molecules. And you notice they all kind of wander over a range of about 10 to 12 parts per million. So you can see that. And so when you put these things in a magnet, which is what in the old days, was NMR. Now it's called high frequency NMR, I guess. I'm not sure what do we call NMR anymore, Joe? In any case, you can actually get very sharp lines, and you learn a lot about the structure of the molecule. And here's, for example, just an example of carbon. Carbon has a much bigger range of chemical shifts because it has 6 electrons involved instead of only 1. And for example, here's a carbonyl out here at about 170 parts per million, and here's a more normal HOH, whatever carbon around in here. So there's a lot of information. So let's just ask what the chemical shift of ethanol would be. See, I told you I was going to bring up ethanol. Ethanol is a very important molecule. So we have 3 kinds of protons, right? We have a methyl-like proton. We have something that's a methylene, and then we have a hydroxyl, right? So in principle, the binding, the effective susceptibility of the electron clouds around these guys is going to be different. And indeed, that's exactly what you see. This is what's called a high-resolution NMR spectrum this is the methyl over here, this is the methylene over here, and this is the hydroxyl. Now you'll notice these are a little more complicated than you might have expected because this has got 1 peak, this has got 4 peaks, and this has got 3 peaks. Why is that? Well, the reason for that is something called J coupling, and basically it's because the protons, this pair of protons here, sort of look like a spin 1 particle, because there's 2 of them and they're identical, and they talk to this triplet over here. And so that depending on whether this is oriented one way or the other way, you get a triplet. That's why this 3 guy has 3 things. It can be up, down, or in the middle. This, on the other hand, now this has now spin 3 halves as a 3, because there are 3 1/2 particles here. And so now there are 4 orientations that are possible, which gives you these guys having a quartet-like structure, because it depends on the orientation. I'm not going to, the underlying physics behind why that happens is kind of complicated. It involves the nuclei talking to the electron cloud, which has to then talks to the next electron cloud, which then talks to the next nuclei, and it all has to do with trying to keep the symmetries involved because of things. Okay, I think I'm done. Oh, sorry, just an example. So just water. This is water and this is fat in the spectrum from somebody's arm. Just to show you what happens when you fat versus water imaging. This is looking at the fat in somebody's hand through the metacarpal right here. And this is looking at the water. And this is the same thing here, but now looking this way. So in point of fact, you can look at 2 different things. Normally, we just look at the water because that's the way we are. And that's the J coupling, which I mentioned, and I'm stopping. Oh, and a bunch of range of J couplings. So there's information in the geometry of how the relative protons are arranged, which is sort of summarized there. But it's quite a complicated analysis. Okay, so I'll stop there. Thank you.